Paul Cézanne claimed that art is a harmony parallel with nature, and nothing demonstrates this idea more than a mathematical triangle born out of poetry. Now, I know the idea may sound ridiculous and even comical, but what we know today as Pascal's triangle started as a desire to better understand Sanskrit prosody. To really understand, we're going to have to go back in time to approximately 300 years before the Common Era, which is around the same time that Euclid lived. Now, during this time, India was ruled by the Mauryan dynasty, which was the first empire to unite most of India under one administration. It was under this administration where art forms were able to flourish and literature was developed. It was in this society that Acharya Pingala, the earliest known person to ever describe Pascal's triangle, lived in. Now, Pingala himself was deeply interested in and even founded the field of Sanskrit prosody. Sanskrit prosody is centered around the study of poetic meters and verse in Sanskrit. It's one of the 6 studies that are essential to understanding the Vedas, which are the ancient Indian texts that are foundational to Hinduism. The Vedas are written in different meters or poetic rhythmic structures. In one of his works where he studies the composition of these meters or rhythmic structures that the Vedas are made up of, Pingala actually discovers some interesting relationships between what he calls the short Lakhu and the long Guru syllables that make up these meters. Even though it isn't directly related to the arithmetical triangle, one of the discoveries that Pingala makes is actually the binary system. And if you aren't already aware, the binary system is basically like the groundwork or the building blocks of basically all computers. Instead of ones and zeros like we have today, what Pingala used as the basis for his system were the short and long syllables. Not only that, but Pingala also found rules for combinatorics. For example, he found a way to computate and figure out the amount of ways to choose k objects from a group of n objects. The way that he actually found this out in the first place was by asking himself the question, how many ways or in how many different ways could a Vedic meter be composed with a given amount of Lakhu, short, and a given amount of Guru, long syllables? Now, if you're just being introduced to this type of problem, it might be confusing, but another way to think about it is by asking yourself the question, in how many ways can I take the words within a letter and rearrange them so that I get an entirely different word? For instance, let's say I give you the word cat, and I want to figure out the amount of ways I could rearrange the letters so that I get a different word, even if they don't make sense. So we have cat for one, or I could have ACT, act, or I could have TAC, tack. And there's a total of 6 ways to do this, but what Pingala was trying to figure out was a general or more holistic formula for figuring out the amount of ways to rearrange short and long syllables within a verse. But instead of rearranging the letters within a word, what Pingala was doing was rearranging the syllables within a meter, or basically a sentence. Now, in Pingala's work, which I can't really pronounce, I'm probably going to put it on screen right here. He included instructions on how to construct what he called Mount Meru's triangle. And even though it wasn't originally acknowledged by many people, a mathematician centuries and centuries later, I think around 1300 years after him in the 10th century, by the name of Halayudha, a mathematician, would go on to claim that that triangle actually formed what we know today as Pascal's triangle. We only know this because Halayudha wrote a commentary on Pingala's original work where he aimed to make Pingala's ideas more clarified and more well known. Constructing the arithmetical triangle itself is actually not that hard. First, you start with a 1 at the top, and then you follow it with 2 ones below it on the next row. And then on the following row, and for every row after, you put a 1 to the very left of the row, and then a 1 to the very right of the row. And whatever is in between those ones is filled in by the sum of the 2 numbers on top of it. So the third row, or the second row of Pascal's triangle, would be 1, 2, 1, because 2 is the sum of 1 plus 1, the 2 numbers above it. According to Halayudha, these are the exact same instructions that Pingala gave to construct his Mount Meru triangle. But Pingala was far from the only person who acknowledged the applications of this triangle. In fact, centuries after Pingala's time, but also centuries before Halayuta's time, an Indian astronomer by the name of Varahamihira, if I mispronounced that, he lived in the 6th century, and he actually used Pascal's triangle in a different manner than Pingala and Halayuta did. Instead of using the triangle to solve problems centered around combinatorics and rearranging things, what Varahamihira did is that he used the triangle so that he could calculate the coefficients of binomial expansions. Now, that may sound like a mouthful if you're not really familiar with binomial expansions, but all it really means is that what Varahamihira did is he looked into the expansion of a plus b to the n power, where n could be 1, 2, 3, 4. Normally, if n is 2, it's easy to computate. You could just use the brackets, split it up, and then multiply the binomials. But once you get to higher powers like 7, 8, 9, it gets harder and harder. Varahamihira is one of the first people to notice that the coefficients, when you expand binomials up to higher powers, they actually correlate to the numbers on the arithmetical triangle. Like, for example, if you take a simple one like a plus b to the 2nd power, you get a squared plus ab plus b squared, or in other words, you get a squared plus 2ab plus b squared. And the coefficients for a squared is 1, for ab the coefficient is 2, and for b squared the coefficient is 1. These coefficients match up with the numbers on the 2nd row of Pascal's triangle. The people who discovered the properties of this triangle were not only separated by time, but also by great distances. In fact, during the 10th century, 14 entire centuries from Pingala's time, a Persian mathematician by the name of Al-Kharajhi also wrote instructions on how to construct a triangle. Even though his work is now lost, his method to construct the triangle was recorded in the works of Al-Samawal, who was an Islamic mathematician from the 12th century. Even though Al-Kharajhi helped to develop a better understanding of the triangle, he also helped in other aspects of math too. For instance, even though he didn't use a fully formalized method, he's one of the earliest recorded people to ever use mathematical induction to try and prove his statements. Also, he's the first person to state the rules for monomials like x squared, x, and x cubed, and their opposites like 1 over x squared, 1 over x cubed, and 1 over x, and the rules for adding and multiplying them. But what Al-Kharajhi is arguably most known for is his presumed introduction of the binomial theorem centuries and centuries before it was formally introduced to the world. The binomial theorem is basically just a more general formula for figuring out all the terms within a binomial expansion without having to manually multiply all the terms together. Now, this is incredibly useful because multiplying binomials manually by multiplying the brackets actually becomes exponentially harder as you go higher in powers. But with the binomial theorem, we could just skip entirely that expanding process and get straight to the result. Binomial expansions also have another property, which was observed by the poet, astrologist, and mathematician Omar Khayyam. The property is that they could be used to extract roots of numbers, whether it's the square root, cube root, or the nth root. What's become a recurring theme, Al-Kharajhi's book on this method has ultimately become lost, and the only description we have on his method is a reference to it from another work of his. Still, Omar has some other notable achievements. For instance, he calculated the length of a year and was actually precise up to the 6th decimal place. Also, he wrote some beautiful poetry. In fact, he's best known for his work in poetry rather than his work in math. It's not hard to see why, especially when you start looking through some of his quotes. If you were to take a step back from Iran and instead travel towards China within the same century, you find that similar acknowledgments for this triangle started to develop there. More specifically, Jia Shan, who was a Chinese scholar, was the first recorded person in China to describe the method of forming the triangle. Jia Shan was born around 1010 and lived during the Song dynasty, which was a period of innovation for China. This is the time period where they developed gunpowder, movable type printing, and the first instance of banknotes, or what we know today as paper money. China even had its own ancient mathematical text in the same way that ancient Greece had Euclid's Elements. The name of this text was the 9 Chapters on the Mathematical Art, and its origins have been traced back all the way to the 10th century before the Common Era, with its latest stage being from the 1st century. Jia Shan wrote a book where he gave detailed solutions on the problems in the ancient texts and presumably used the arithmetical triangle in a similar manner to both Al-Karaji and Omar Khayyam. To no one's surprise, this book is now lost. However, we know about his uses of the triangle because of Yang Hui, another Chinese mathematician who wrote a book to make Jia Shan's work known during the 13th century. In fact, today the triangle is known as Yang Hui's triangle in China. According to Yang, Jiasha knew about the expansion of a plus b to the n power and gave a table of the matching coefficients of the terms in the form of the arithmetical triangle. This process should seem familiar because this is what Varahamihira did. Additionally, Jia also used the triangle to come up with his own method of extracting nth roots, which would later be known to the world as Horner's method. This goes to show how this triangle is really some sort of disconnected group project. Eventually, the triangle also reached Europe. Whereas mentions of this triangle in texts were few and far between in other parts of the world, the triangle has been documented by numerous people in Europe. The introduction of it to Europe was through Jordanus Nemoret's book titled De Arithmetica. Although little is known about his life, we do know that he was a German mathematician who lived within the same century as Yang Hui, namely the 13th one. Even though many details about his life are unknown, he's made considerable contributions to astronomy and physics in addition to his ones in math. Within his De Arithmetica, he gives somewhat cryptic instructions on how to construct the arithmetical triangle, but the fascinating detail is what Jordanus notices about the triangle itself. He acknowledges that the sum of the rows in the triangle form a continued proportion with a factor of 2. In other words, the sum of all the numbers in each row of the triangle are consecutive powers of 2. This is why I referenced the initial row of the triangle as the 0th row earlier, because 2 to the power of 0 is 1, and therefore that row would be called the 0th row, and the one after that would be called the 1st row, and so on and so forth. Aside from Jordanus, this arithmetical triangle was briefly referenced by other Europeans like Gersonides, Petrus Appianus, and Michael Stifel. By 1556, the triangle appeared in Part 2 of Niccolo Tartaliga's General Trattato di Numeri et Misure. Niccolo knew about how to construct the triangle and its relation to binomial expansions. In Italy, the triangle is actually named after him. It's similar to how Yang Hui had the triangle named after him in China. Later, a little over a century after Tartaglia's publication, word of the arithmetical triangle finally reached Blaise Pascal. Like the countless other mathematicians who came before him, Pascal was innovative and curious in his approach to life. At the age of 17, he caught the attention of René Descartes with his essay on conic sections. Even in his early 20s, he developed one of the earliest mechanical calculators just to help his father perform tax calculations. The reason why the triangle came to be associated with Pascal, even though it didn't originate from him, is because he contributed the most to our understanding of it. He did this by culminating the already existing knowledge of the triangle in his quote-unquote treatise on the arithmetical triangle, which was published in 1665, as well as connecting numerous aspects of the triangle to probability. For example, Pascal pointed out that each number on the triangle represents the number of ways to choose a certain number of objects from a larger group. Through this, Pascal was able to come across combinatorial identities like what we know today as Pascal's identity, and the fact that the sum of all n choose k from k equals 0 to k equals n is just 2 to the n. Because of Pascal's contribution, future mathematicians were inspired to find even stranger patterns within the triangle. There are way too many to talk about considering that this video is already almost 15 minutes long. However, some unexpected patterns that can be found in the arithmetical triangle include the Fibonacci sequence, figure 8 numbers, and even the Sierpinski triangle. In fact, we're still finding new patterns. We call the triangle Pascal's, but is it really his? I think we should call it the Pingala, Halayuta, Karaji, Khayyam, Xian, Yui, Tartaglia, Pascal triangle, just for simplicity's sake.